Imagine that everything around us, everything we experience in daily life, is defined by three dimensions of space: forward, backward, left, right, and up, down. These three directions are all we know when it comes to movement. But scientists have long speculated that there could be extra, hidden dimensions beyond these three. We can't see them, and they don't affect us directly in daily life. But what if we could somehow access them? That's where our hypothesis comes in. What if we could move in a fourth dimension using rotation? Here's the step-by-step breakdown. 1. Rotational inertia. What is it? When you spin something, whether it's a top, a fan blade, or even the Earth, the object doesn't just keep spinning forever without effort. It resists changes to its motion. This resistance is called rotational inertia, or simply inertia. The bigger and more massive an object is, or the more spread out its mass is, the harder it is to spin and the more inertia it has. Think of it like a spinning wheel. The more weight it has and the further that weight is from the center, the harder it is to get it spinning and the more it resists stopping once it's going. That's inertia in action. But here's where it gets interesting. We're proposing that rotational inertia isn't just a passive resistance to change in motion. Instead, it might actually hold the key to interacting with higher dimensions. What if rotating something in a very controlled way could allow us to tap into a dimension beyond the three we know? Instead of just spinning in 3D, it could move or interact with a hidden fourth dimension. 2. Curved space-time. Understanding gravity. To make sense of the idea of moving in a fourth dimension, we need to understand how gravity works. Normally, we think of gravity as something that pulls things toward the Earth, but what's really happening is that gravity bends the fabric of space-time itself. Imagine space-time like a trampoline. If you place a ball on the trampoline, it dips and forms a curve, right? Now, if you roll a smaller ball near the bigger one, it'll roll towards it because of the curve. The bigger ball is creating a dent in the trampoline. That's what gravity does. It bends space-time, creating a curve. And when objects move through this curve, they follow paths that are altered by the bending of space-time, what we call geodesics. But here's where our idea goes beyond the usual concepts of gravity. What if this bending doesn't just affect things in 3D space, but also could let us move in a hidden fourth dimension? 3. The fourth dimension. What is it? Now let's think about this fourth dimension idea. In our everyday lives, we only experience three dimensions of space: length, width, and height. But in theory, there could be additional dimensions beyond what we can see or feel. Scientists who study things like string theory or quantum mechanics often talk about these hidden dimensions. But since we don't have a way to directly observe them, they seem abstract and unprovable. What if rotational inertia could be the key to revealing or interacting with this hidden dimension? Here's our big idea. We're suggesting that rotating objects could somehow interact with these extra dimensions by coupling their rotational motion with the curvature of spacetime itself. When an object rotates, its inertia resists changes to its motion, and this resistance could allow it to move or shift into the fourth dimension, just like an object moves through 3D space. 4. How can we test this? If this hypothesis is true, it means we could test the idea of accessing the fourth dimension through rotation by carefully controlling how we spin tiny objects. Here's how it could work. Rotating a tiny object, like an atom or nanoparticle. First, we need a very small, controlled object. It could be something like a levitated nanoparticle or a cold atom, which can be precisely rotated using lasers or magnets. These tiny objects are ideal because we can control their rotational motion at the quantum level, meaning they respond to very small changes, creating curved spacetime. Next, we need to simulate a curved spacetime field around the object. This could be done in a lab by using things like rotating fluids or photonic crystals, tools that can create effects similar to the curvature of spacetime. Alternatively, we could use electromagnetic fields to simulate how space might be bent in small regions. Observing the object's movement. Once the object is in a controlled environment with the right rotational inertia and simulated spacetime curvature, we'd track its movement. Normally, objects follow predictable paths, but if they interact with a fourth dimensional axis, we might see strange shifts in how they spin or unexpected changes in their position. 5. Why does this matter? If this idea holds true, it could revolutionize several fields. Space travel. The ability to interact with the fourth dimension could mean that we find a way to travel through space more efficiently, bypassing the need for traditional propulsion methods. Instead of pushing against 3D space, we could manipulate the very fabric of space-time. New energy or technologies. Understanding how to manipulate inertia and curvature could lead to new energy sources or even completely new types of quantum computers. Instead of using the physical space for processing information, we could use higher dimensional space, potentially making our systems more powerful and efficient. New discoveries in physics. If we could prove the existence of higher dimensional spaces, it could reshape our entire understanding of gravity, quantum mechanics, and the fundamental nature of the universe. Summary of the concept. In simple terms, this hypothesis proposes that by rotating objects in a specific way, we might be able to access a hidden fourth dimension, a new spatial direction we can't normally perceive. If proven, this could lead to groundbreaking advancements in everything from space travel to quantum computing by giving us new ways of understanding and manipulating the fabric of space-time itself. Takeaway. This idea, while currently speculative, could open doors to a new realm of possibilities for science, technology, and even our understanding of reality itself. If the right experiments show that rotational inertia can truly couple with space-time curvature to open up new dimensions, we'll be looking at a fundamental shift in how we interact with the universe. If you like this analysis, please like, subscribe, and leave a comment. We would love to hear from you. And don't forget to hit the bell for upcoming videos. Thank you for watching.